For the purists in the group, technically what you get at the end is what is known as an axial vector or a pseudo-vector. However, as far as we are concerned in this course and in Physics 152, actually if you were in 251 and 252, the same thing, pseudo-vectors slash axial vectors smell, taste exactly like regular vectors. So the distinction gets into much higher up between the two. It has something to do with reflections, so you don't have to worry about that. Dot products are called dot products because the multiplication symbol you use is a dot. A cross product, the symbol that you use, it's really an X, but they call it a cross. At some point in math, you're told that both of these mean multiplication. When you're dealing with vectors, there is a distinction between the two. When you multiply vectors, vectors have components. So if I have a vector that's like that, I've got a part that's going, say, to the right and part of it's going up. If I want to multiply this vector times another vector, the question is, how do I multiply that vector with, say, a vector that's going like that? Because this vector also has a horizontal and a vertical component. Well, I can multiply parallel parts. These would count as parallel, technically anti-parallel. You multiply parts that are basically along the same line, or you can multiply parts that are perpendicular to each other. Dot products, you're multiplying the parallel parts. With the cross product, you multiply the perpendicular parts. And then, side note, dot products are also called inner products. So we would take a wild guess what cross products are also called?
Outer products.
Yes. I believe technically inner products and outer products are more generalized forms of them. But if you ever run across inner products, think, oh, I'm just multiplying parallel parts. All right, so that's the distinction. We're gonna, unless there's a question about it, we're going to sort of ignore cross products for a month or so. All right, let's talk dot products more specifically. If I have a vector here, A, and a vector here, B, I want to multiply parallel parts. I have some angle between them, theta. And so I'm going to take one of my vectors, and it doesn't matter which one. I'm going to take one of the vectors, I'm going to break it up into its components. I'll have a vector that way and that way. I know the magnitude of this vector is A. I have this angle theta here, so this is A cosine of theta. This is A sine of theta, using right triangle trait. So if I did A dot B, I multiply the parallel part, so I multiply B. I multiply the magnitude of B times the magnitude of the part of A that's in the same direction, A cosine B, or A cosine theta. So A dot B is just AB cosine theta. So if you get the vectors in polar form, this is the simplest way of doing it. So for example, if A is 5 newtons, 40 degrees, and B is 3 meters, 120 degrees, then A dot B is just the magnitude of A times the magnitude of B times the cosine of the angle between them, which would be 80 degrees. Just the difference in the angles. And this is something small, because cosine of 80 degrees is a small number. I'm just gonna pretend cosine of 80 degrees, let's just pretend that's equal to 0.1, unless somebody tells me otherwise. Then we'll pretend. And so you'd end up with 1.5 Newton meters. Also bringing out the fact that when you are multiplying units, put a dot in between them. Now, in the case of if you write Newton dot meters, or Newton meters, because the capital N is not some known prefix, you actually could get away with this. However, if you want to flip it around and write meter Newton, a meter Newton would be written like this, but if you drop the dot, that suddenly becomes a millinewton, because M is a known prefix. So the dot is for clarity, as opposed to, if you wrote this, the person reading it might look at it and go, wait, is capital N a prefix I don't know about? It's a prefix I don't know about. So those you might get away with, those no. Now notice, it doesn't matter the order in which I multiply these. Let's take our A and B again. So if I have A going up like this and I have B going like that, I could break angle theta in between them. I could break B up. I could break B up into its parts. I got part of it going this way and part of it going that way. Using the right triangle trig, this would be the magnitude B sine of theta and B cosine of theta. And so I multiply the parallel parts, so I would get A times B cosine of theta, which gets me back to the exact same spot. What I'm getting towards there is the order in which I do a dot product does not matter. For the math fans out there, the commutative property of multiplication holds for dot products. And this dramatic pause for questions. All right, one more bit about dot products and then we'll get back to the cake. So some people are ready, I will erase some of this. If I take a vector and do a dot product with itself, I basically have A dot A. It's going to be the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So this would be A times A. What is the angle between a vector and itself?
0.
Times the cosine of 0. Radians or degrees, depending upon your mood. What is the cosine of 0? So this is just A squared. I think now we are ready. So what I want to do, I'm first going to take our displacement is equal to VI plus VF over 2 times time. This equation right here. I am also going to take acceleration, which is VF minus VI over time. The numerator there for acceleration, that's just a change in velocity. I'm now going to multiply. I'm going to multiply the left sides, I'm going to multiply the right sides. Because the math people insist, as long as they do it the same, if I multiply both sides by the same thing, I'm good to go. So I'm going to multiply those two together, I'm going to multiply those two together. So I end up with acceleration times displacement equals VI plus VF over 2 times time. Dot product, VF minus VI over time. My times will cancel out. I got multiplying by time here, dividing by time there. Time goes away. The 1/2, again, constant dot products deal with multiplying vectors. This is a scalar here, so I'm just gonna factor it out. Actual fact, I'm just gonna multiply both sides by 2 to get 2 over here. So I now have 2a dot delta x is equal to VI plus VF. Dot product, VF minus VI. Now, I have 2 binomials, 2 vectors expressed as binomials. I'm doing a dot product. What would we do in algebra?
FOIL.
Yep. So if I multiply the first ones, looking at just the right side, I get VI dot VF. Outer minus VI dot VI. Inner plus VF dot VF. Last minus VF dot VI. Take a moment to convince yourself if that's right, or ask if you missed something. Now, if this were a cross product, keeping the order would be crucial. It's a dot product, so it doesn't matter the order in which you multiply. So this VI dot VF and VF dot VI, those are the same thing, except I'm subtracting. So those are going to cancel out. What I'm left with is a vector times itself. So this becomes negative, go for something better than that, negative VI squared plus VF squared. Because a dot product with itself is just the magnitude squared. So I'm now left with 2a dot delta x is equal to VF squared minus VI squared. Or more traditionally written, we'll add VI to the other side, and I have VF squared is equal to VI squared plus 2a dot delta x. And we now have our fourth one. What's that? Some textbooks, I don't think yours does, but some textbooks will throw in a fifth equation. To get the fifth one, you solve for VI here and plug into this equation, and you get a fifth one. I tend not to do that, but we can make do with what we have here. All right, notice. Each of these is missing something. This equation is missing the displacement. This equation is missing acceleration. This equation is missing the final velocity. This equation is missing time. And the fifth one would be missing VI if it did it. But this allows us that if we have a problem that we're trying to solve, turns out if I know 3 things, I can find the other 2. So for most of these problems in chapter 2 and 3, I have 5 quantities I'm messing with here. Potentially 6 if we wanted to split displacement up into initial and final position. But 5 quantities that we were working with here, and we need to, and pretty much all problems are solving this. A ball is thrown upward initially at 25 meters per second. It's about 54 miles an hour. At what time will the ball reach its peak? And how high above release will the ball be at its The first thing to do when solving a problem like this is identify what we know. We need to be able to figure out three things. So, given the problem, what do we know?
The speed it's going at.
The initial velocity.
What was that, Giovanni?
The initial velocity.
Initial velocity, okay. What is the initial velocity?
25 meters per second.
What did you assume?
So it's not that?
Pardon?
It's not that?
Oh, it might be, depends on your assumption. He made an assumption, anyone else can join in. He said that the initial velocity was 25 meters per second. But there is an assumption built into that.
Well, it says initially, I thought the same thing.
That it's positive.
Why, what's the deal with positive? I didn't see you spoke.
As, it doesn't specifically say positive,
So, therefore, what was the assumption he made?
that it was positive, or going up.
All right, let's combine those two. Dominic, were you about to say it?
Okay, so.
All right, it does say 25 meters per second. That 25 meters per second right here is the initial speed. We have to somehow indicate the direction. We have this upward thing here. If we assume up is positive, then Giovanni is absolutely right. That was the assumption he made when he said the initial velocity was 25 meters per second. If you want to make down positive, then my initial velocity is negative 25 meters per second. But we do need to establish what is the positive direction. So if we make up positive, then 25 meters per second is the initial velocity. All right, there's one other piece of information. Actually, there's two other pieces of information implied in the problem. Well, one definitely, and the other one, we will make an assumption. Dominic?
The assumption B that its initial disposition is at 0.
Initial position?
Yeah, the initial position's at 0.
We can, that's not going to affect anything, because ultimately we're trying to figure out how far above point of release the ball goes,
Okay.
so. But if you want to make that assumption, there's no harm in it. What do you know about it? We're trying to figure out how much time it takes for the ball to get to the top. What happens at the peak?
It goes back down, the velocity goes to 0.
Yes. The peak is the point in which it changes direction, and you cannot change direction. You're going from a positive velocity to a negative velocity. You have to go through 0. At the peak, it stops for a brief moment before it starts coming back down. So my final velocity, 0 meters per second. Yes,
So that'd be the last, like, one would be at its peak is when, in the equation, when the final velocity is 0 is when it's at its peak.
yes. Assuming it's a one-dimensional problem. And we can assume that because the ball is thrown upward, not at an angle. I guess to make that clear, straight upward. There's one other bit of information that's implied in this. Typically, I don't do the ball being thrown into the air examples first, but I was inspired. Once we are ignoring air resistance, if you want to bring air resistance into it, have fun. If you don't have calculus and you want to bring air resistance into it, yeah, good luck. You would be a masochist. It's bad enough with calculus. But we are going to ignore air resistance. Once the ball leaves the hand, and some students don't buy it, but I'm just going to let you in on a secret here. Jedi powers do not exist in this course. Now, you might even be able to experience Jedi powers on your own in your own bedroom, but here, Jedi powers are not working. We'll make that assumption for the whole course. Once it leaves the hand, what is the only thing exerting any force on it?
Gravity.
Gravity.
I'll buy that for now. Later on, I will nitpick that. If the only force acting on it is the force due to gravity, then the acceleration is constant. We'll get into nuances later. For the sake of anything close to the surface of the Earth, it is close enough. Now, officially, the acceleration due to gravity at the top of this building and at the ground are different, but you need multi-million-dollar equipment to measure that difference. So we will assume that anything that we are dealing with here up until once you get to outer space, so once you're 100 kilometers up, the acceleration due to gravity has